next part is the Arrhenius equation. Arrhenius equation. This equation also gives the same thing, that is a relationship between the temperature and the rate of reaction. This reaction tells us about the theoretical proof which gives the relationship between the temperature and the rate of reaction. Instead of rate of reaction, I can say it gives the relationship between the temperature and rate constant. Now let's see what is the Arrhenius equation here. So the equation is Arrhenius equation is K is equal to A into E raised to minus EA upon RT. This is the Arrhenius equation given in the exponential form. Now let's in the log form. So taking a log on both sides, so this E will be removed. So taking a log, here I will get, since it is an exponential form, so we will take a log to the base E. That means we have to take exponential log on log to the base E, that is. So log to the base E, which can also be written as ln. So it will be ln K is equal to ln A. This is the antilog of minus E raised to minus EA upon RT. It means it is antilog of EA upon RT. So minus, if I'm taking a log, then antilog will removed. So minus EA upon RT. So we have this as a Arrhenius equation in a log form. Here the ln K is equal to ln A minus EA upon RT. Now what is K? Then I will say K is a rate constant. What is A? I will say A is called as, it is again a constant which is known as a frequency factor. Again A is constant. The unit of A and K is same. If the K, unit of a K depends on the order of reaction. If the reaction is a first order, the unit is per time. If the reaction is zero order, it is going to be m raised to 1 minus n per time. That is m raised to minus 1, m raised to 1 per time. So the unit of A depends upon the unit of K. Now ln K is equal to ln A minus EA upon RT. Now here the factors, the terms are, as I said, K is a rate constant. EA is a frequency factor, that is again a constant only. EA is called as a activation energy. R is a gas constant, universal gas constant, or I can say whose value is 8.314 joules per Kelvin per mole. And if I'm taking R in a joules, so in a formula activation energy should also be in a joule only. And T is the absolute temperature. Absolute temperature means temperature in Kelvin. Now here the log, we have a formula, that is we have this Arrhenius equation but in the form of ln, that is log to the base E. Now let us write it in the form of log to the base 10. Now in the last time we did a derivation in which I said that ln, if you wanted to convert a ln into log to the base 10, then multiply the equation by 2.303, that is ln is equal to 2.303 log to the base 10. So here ln K will become log to the base 10 K is equal to log to the base 10 A minus EA upon RT. There is a no ln, so no need to multiply. It will be 2.303 also, because we are having ln, we are converting ln to log to the base 10. And this here also we will have 2.303. So we have 2.303 here as well as here. So let us remove 2.303. So dividing by 2.303. So if I am dividing, then I will get log to the base 10 K is equal to log to the base 10 A minus EA upon, due to the division we will have 2.303 RT. So we got this another equation. This equation generally we use for solving numericals based on Arrhenius equation. Now I said Arrhenius equation gives a relationship between the temperature and rate constant. Now if I am saying here how this equation also tells us that as the temperature increases, the rate constant also increases, and hence the rate of reaction increases. How? Let's see. See, if I am increasing a temperature, what will happen if I am increasing a temperature? This full factor will decrease. Temperature is in denominator. So if I am increasing a temperature, then what will happen? The fraction value will decrease. I will get a small value. If I am getting a small value, means ultimately I am subtracting a small value from ln, and if I am subtracting a small number, then ultimately the left number is going to be larger one, and that left number will be nothing but k. So I can say that if the temperature is increased, then k is also getting higher. The value of k is also high. Suppose if I am taking if the temperature is decreased, temperature decreases means the denominator decreases. So ultimately the fraction value will be high. Fraction value is high means you have to subtract a large number. And if you are subtracting a big number, then ultimately the left number after the subtraction will be small. And left number is a small, that is a k value will also small. So the Arrhenius equation also tells that temperature and rate constant, they are directly proportional to each other. So here also I can say that if I am increasing a temperature, the rate constant value also increases. Now, suppose if I am plotting a graph of this, here the log to the base, let's see the graph of this. We have Arrhenius equation, log to the base 10 k is equal to log to the base 10 a minus EA upon 2.303 RT. This equation somewhere looks like comparing with y is equal to mx plus c. This is going to be on y-axis, this is going to be c, this is going to be on x-axis, and this whole term, that is this term, is going to be m, that is slope. So if I am plotting a graph of log to the base 10 k versus 1 upon temperature, then the graph is going to be a straight line, because it is the equation of the graph is like a y is equal to mx plus c. So the graph is going to be a straight line with the negative slope. Slope is a negative, means the graph is going to be from top to bottom, and we have c value also. C value also means we have y-intercept also. So the graph is going to be something like this, right, with the negative slope. Here the slope is equal to, we have minus EA upon 2.303 R, and this y-intercept is log of A. Means with the help of graph, again I will get the two things. I can calculate the value of frequency factor, that is A. Whatever the number we are getting from the number, we will get log A. And from the graph, even I can calculate activation energy. How? Suppose from the graph, the slope is equal to, from the graph I will get the value of slope. So I wanted to know the activation energy. So activation energy is going to be, transfer all the number on this side, slope, minus sign will also come, into 2.303 into R. I know the value of, I will get the value of slope from the graph. R is 8.314, 2.303. So you will get the value for the activation energy also. Okay, so this is about the Arrhenius equation. Here in Arrhenius equation, this term, that is minus e raised to minus EA upon RT, e raised to minus EA upon RT, is known as Boltzmann constant. And this graph is known as Boltzmann distribution curve. So just keep in mind that this is Boltzmann constant. If sometime it is asked, Boltzmann constant e raised to minus EA upon RT. Now, as I said that on increasing a temperature, the rate constant also increases, or if I'm decreasing a temperature, then rate constant also decreases. So there is a variation takes place between, so if there is a relationship between the K and temperature, we all know. So now we have a formula which tells us that how much rate constant changes if the temperature is increases by some number, and that formula has been derived by using Arrhenius equation. Means we get this formula on the basis of Arrhenius equation. So now let's derive that formula and let's get that formula from the Arrhenius equation. So Arrhenius equation, variation. We have our Arrhenius equation. So what is the equation now? So Arrhenius equation is log to the base 10 K is equal to log to the base 10 A minus EA upon 2.303 RT. Now let I'm changing a temperature from T1 to T2, where the T1 is a lower temperature and T2 is a higher temperature. Now let's see what things or what factors will change if I'm changing a temperature. If I'm changing a temperature, we all know that K is going to be changed, because K, that is a rate constant, depends only on one factor, that is called as temperature only. So this will change. A is a constant, it does not depend on temperature. So simply I can say that on increasing a temperature, the A value will not change. What about the activation energy? Again, activation energy does not changes on increasing or decreasing a temperature. That means it is independent of temperature. So activation energy will also not change. R is a constant, so again it will not change. T, we are changing. So I can say that on increasing a temperature, only one factor is changing from the formula throughout, that is only K. So here I can say that I am changing a temperature from T1 to T2, where I said T1 is a lower temperature and T2 is a higher temperature. And if I'm changing a temperature, the K will also change, and let the change in the, so I can say K1 and K2 are the two constant, where K1 is a rate constant at temperature T1 and K2 is a rate constant at temperature T2. So K1 and K2 are rate constant at temperature T1 and T2 respectively, where I can say a very important thing, that is T2 is greater than T1. It's a very important. T2 is greater than T1 means in a formula, when the after the derivation, the formula which we will get, in that formula, whenever we are going to substitute the values of T1 and T2, always keep in mind that T1 and T2, out of T1 and T2, T2 should be higher value and T1 should be lower value. It should not be like the term, the temperature which is written first in the numerical will be T1 and the one which is written after is T2. Such thing is not to be considered here. T1 and T2, that is T2 should be higher temperature, and if the T2 is a higher temperature, means K2 will be the higher rate constant, K1 is going to be the smaller rate constant. So let us write the same equation in terms of K1 and K2 and T1 and T2. So this will, if the rate constant is K1, so the formula will be log to the base 10 K1 is equal to log to the base 10 A will not change minus EA upon 2.303 RT1. Like this is equation number 1. Similarly, in second case, log to the base 10 K2 is equal to log to the base 10 A minus EA upon 2.303 RT2, equation number 2. I wanted to club both the equations. So let us club. Clubbing will be done by subtraction. So equation 2 minus equation 1. So equation 2 minus equation 1. So if I'm subtracting, it will become log to the base 10 k2 minus log to the base 10 k1 is equal to, during a subtraction both are same, so it will get cancelled. We will get this minus this. So minus EA upon 2.303 R T2 minus of minus. We are subtracting, so minus, and this term is also having a minus sign. So minus EA upon 2.303 RT1. Therefore, subtraction so can be written in the division form. So it will be log to the base 10 k2 upon k1 is equal to, minus minus will become plus. So let us write that first, that positive term, that is 2.303 R T1 minus EA upon 2.303 R T2. Something is common, so we can calculate log to the base 10 k2 upon k1 is equal to, the common terms are activation energy upon 2.303 and R, and then 1 upon T1 minus 1 upon T2. Therefore, I can say log to the base 10 k2 upon k1 is equal to activation energy, that is EA upon 2.303 R. This can be written as T2 minus T1 upon T1 into T2. So this is the formula which we finally get. So this is the formula which we finally get. So if I'm changing a temperature, that how much rate constant will be changed can be determined by using a formula. This formula is also used for calculating the activation energy also. That on, if change the temperature, K value will be changed, and hence from that data we can calculate activation energy too. So this is the Arrhenius equation and temperature variation. If you are changing a temperature by 10 Kelvin, just use all the relation with the activation energy. You will come to know that K2 upon K1 is equal to twice 2 to 3. Means if you are changing a temperature by 10 degrees Celsius, the difference is 10, whatever the temperature. Just use a formula, and when you will calculate K2 upon K1, you will get that difference is that K2 upon K1 answer is between 2 to 3 K2 upon K1 value, because K2 upon K1 is nothing but the temperature coefficient. We just did the formula for it.